Hubble just found a black hole it was never supposed to be able to find. Confirmed that our nearest large galactic neighbor is slowly, quietly winding down. And caught a galaxy doing something 12.4 billion years ago that directly rewrites how scientists think the first stars lit up the universe. All three of those happened within about 6 weeks of each other, between mid-June and late July 2026. And together, they represent some of the most significant results this 36-year-old telescope has produced in years, arriving almost on top of each other from a spacecraft most people assumed had long since been overshadowed by newer instruments. Tonight, we're breaking down all three, one at a time, so by the end, you'll understand exactly why scientists are this excited about each of them, and why the timing of all three landing together matters just as much as any single result on its own. Let's start with the one that dropped on July 13th, 2026, because it solves a mystery astronomers have wrestled with for decades. Inside the globular cluster, Omega Centauri, there are supposed to be roughly 10,000 black holes. That number comes directly from standard models of how massive stars age, explode as supernovae, and collapse inward. Omega Centauri itself is enormous, 10 million stars packed into a sphere roughly 150 light-years across, one of the oldest and largest star clusters orbiting our Milky Way at around 12 billion years old. Many astronomers actually suspect it isn't a true globular cluster at all, but the stripped-down core of a dwarf galaxy our Milky Way swallowed billions of years ago, its outer stars torn away by tidal forces while its dense central nucleus survived intact. That would explain why it's so unusually massive and why it appears to host an intermediate mass black hole at its center, something ordinary globular clusters simply don't have. Given that much mass, age, and violent history, the expected population of smaller stellar mass black holes inside it should have been substantial. The problem was that nobody had ever actually found a single one. Zeros out of an expected 10,000 for as long as astronomers had been looking. Every previous search, using radio and X-ray signals from material falling into a black hole, or a technique called radial velocity that watches for the wavelength shift in a star's light as something invisible tugs it back and forth, came up completely empty, leaving the so-called missing black hole problem as one of the more persistent puzzles in Stellar A-Team led by Matthew Whitaker at the University of Utah tried something different. They went back through more than 20 years of Hubble's archival data, observations stretching from 2003 to 2023, and instead of hunting for radiation, they watched how a single star moved. This technique, called astrometry, tracks a star's precise position over time to see if its path is being subtly tugged by something unseen. The precision required is extraordinary. Over 2 decades, the star in question shifted across the sky by a genuinely tiny amount, and buried inside that motion was a slight wobble, a deviation from what a freely moving star's path should look like. That wobble was the gravitational fingerprint of an invisible companion. Making a measurement this precise requires exceptional image stability, the same reference stars tracked consistently across decades, and an instrument whose calibration hasn't drifted in ways that could fake a signal. Hubble, positioned above Earth's atmosphere with a carefully documented calibration history stretching back decades, was essentially the only instrument on Earth, or in orbit, with an archive deep enough to attempt this. To confirm exactly what the invisible object was, the team brought in fresh observations from the James Webb Space Telescope to sharpen the measurement further, cross-checking their Hubble-based result against an entirely independent instrument. The result, published in the Astrophysical Journal, Letters on July 13, 2026, the invisible object pulling that star is a black hole officially designated Omega Cat BH2, weighing approximately 4.46 times the mass of our Sun. That specific figure turns out to be one of the most interesting details in the entire discovery because it falls squarely inside what physicists call the mass gap, a range roughly between about 3 and 5 solar masses, where neither neutron stars nor the more massive black holes typically detected by gravitational wave observatories tend to appear. Facilities like LIGO and Virgo, which detect the ripples in spacetime, produced when compact objects merge, have found almost nothing in that specific range, leading some theorists to wonder whether something about the physics of stellar collapse makes objects that size difficult to form. Finding one directly, sitting inside a stellar cluster, suggests at least some of that missing population genuinely exists. It just requires a fundamentally different detection method to actually find. The star orbiting this black hole takes roughly 94 years to complete one full orbit, giving the binary system the longest orbital period ever measured for a black hole pair. Another record inside a discovery already full of them. This isn't just confirmation that the models were right about black holes forming inside globular clusters. It's a working proof of concept for finding the other 9,999, with NASA's Nancy Grace Roman Space Telescope scheduled to launch August 30th, 2026. capable of imaging fields as crowded as Omega Centauri, with Hubble's sharpness across a field of view roughly 100 times wider. The research team has said directly that Roman is the tool needed to scale this search from one confirmed black hole to potentially thousands. Now, let's move to the second story, which dropped on July 27th and involves a galaxy most of you could actually go outside and look at tonight. The Andromeda Galaxy, Messier 31, sits about 2.5 million light-years away, our nearest large spiral neighbor, bright enough on a dark night to spot without a telescope. A team led by Tobin Weiner at the University of Washington spent years assembling the most comprehensive star-by-star map of Andromeda ever produced, combining two massive Hubble survey programs, the panchromatic Hubble Andromeda Treasury and its southern counterpart, together requiring roughly 600 separate telescope pointings across more than a decade. The result, a catalog of approximately 200 million individual stars across roughly 2/3 of Andromeda's disk. Co-author Ben Williams explained the reasoning plainly. Stars are effectively the fossil record of a galaxy's formation history, and mapping enough of them in enough detail lets you read a galaxy's biography directly from its population. What that biography revealed, published July 27, 2026 in the Astrophysical Journal. Andromeda's star formation rate has been falling for 500 million years, currently sitting at roughly 1/5 of a solar mass per year, down from about one full solar mass per year 500 million years ago, an 80% decline. And the drop hasn't been steady. Over just the last 40 million years specifically, the decline has accelerated even further. Andromeda isn't dead, it's still making stars, but at a dramatically reduced, still falling pace. Astronomers call galaxies in this state the Green Valley, a transitional zone between actively star-forming blue spirals and fully quenched red galaxies that have stopped forming stars entirely. Galaxies that enter the Green Valley typically keep moving through it in one direction, eventually crossing over and going largely dark. The most likely explanation isn't a lack of raw material. Andromeda still has plenty of gas that could in principle form new stars, but a natural winding down following an earlier, much more active period. Around 2 billion years ago, Andromeda appears to have gone through a dramatic starburst, possibly triggered by a gravitational encounter with a nearby galaxy, consuming enormous reserves of cold gas and leaving the galaxy quieter ever since, like a runner cooling down after a hard sprint. Researchers are still investigating whether Andromeda's satellite galaxy M32 played any role in triggering that earlier burst, or the current decline, work that's continuing alongside ground-based follow-up observations. Now the third discovery, the one that reaches furthest back in time and carries the deepest implications for understanding how the universe as we know it actually came together. On June 23, 2026, a team led by Ilias Guverts at the Space Telescope Science Institute announced Hubble's detection of ultraviolet light from a galaxy, cataloged as MXD-FZ 4.4, that existed just 1.4 billion years after the Big Bang, light that's been traveling toward us for roughly 12.4 billion years. Here's why that matters. After the Big Bang, the universe was filled with hot ionized plasma that light couldn't travel through freely. As the universe cooled, protons and electrons combined into neutral hydrogen, letting light finally travel. But that same neutral hydrogen was opaque to a very specific kind of light, high-energy ultraviolet, photons capable of ionizing hydrogen atoms all over again. The period during which early stars and galaxies gradually strip those electrons back off, making the universe transparent to ultraviolet light permanently, is called the epoch of ionization, and it remains one of the most fundamental open questions in cosmology. Which galaxies drove it, how bright they needed to be, and whether their radiation escaped easily or got absorbed by surrounding gas. Guvert's team caught MXD-FZ 4. In the act, tightly clustered young stars producing ultraviolet radiation, intense enough to ionize and clear the neutral gas immediately around the galaxy, creating a bubble of transparent space at a moment when that process was still actively unfolding across the wider universe. Guverts himself said observing a galaxy like this was thought to be essentially impossible, since researchers expected the surrounding cosmic fog would be too thick to let that light through at all. The detection required the galaxy's ultraviolet output to be strong enough, the specific line of sight through intergalactic space to already be sufficiently cleared, and Hubble's ultraviolet sensitive instruments to catch a signal at the end of a 12.4 billion year journey. Notably, this is a detection Webb currently cannot make. Webb's instruments are optimized for infrared light, while this specific measurement depended on Hubble. There's decades of carefully maintained ultraviolet capability Webb, its current instrument suite simply doesn't cover. That's really the thread tying all three of these stories together. Hubble launched in April 1990, survived a famously flawed primary mirror corrected by astronauts in 1993, and has been operating continuously ever since, through 5 servicing missions and multiple generations of instrument upgrades. Many space telescopes come and go, producing a few years of results before being superseded and going dark. Hubble has outlasted nearly every expectation that existed at its launch, still producing genuinely first-class science that nothing else currently available can replicate. The Omega Centauri result required 20 years of archival data. The Andromeda study required more than a decade of survey observations across 600 telescope pointings. The ionization detection depended on ultraviolet sensitivity Webb doesn't have. Webb and Hubble aren't doing the same job in different ways. They're doing genuinely different jobs, covering different wavelengths and different science entirely, which is exactly why NASA treats them as complementary rather than one replacing the other. With Roman set to join them on August 30th. 2026, all 3 research teams have already pointed to it directly as the instrument that will let them scale these individual results into full surveys, thousands of black holes instead of one, complete galactic maps in a fraction of the time, more ionization-era galaxies than a single detection could ever provide. It's an unusual moment in observational astronomy, a 36-year-old observatory with an archive nothing else can match, about to be joined by one of the most capable new instruments ever built, each covering ground the other simply can't. If you want to know what Hubble, Webb, and Roman find next as all 3 start working in tandem, subscribe and turn on notifications, because a 36-year-old telescope just proved its archive still has genuine firsts left inside it, and there's no telling how many more are still waiting to be found.